Now we're ready to take a closer look at Poisson regression, which is an example of a conditional maximum likelihood model. Recall that we will specify a model of the form y given x follows a Poisson distribution with mean equal to e to the x prime beta. We don't assume that this is the true model. It's just a possibly misspecified model for y given x with which we are going to work. If you recall the probability mass function for the Poisson distribution from our first lecture, substituting in e to the x prime beta for the parameter of that Poisson, which we called theta, we obtain the following log likelihood function, which again is a conditional log likelihood in terms of x. I may not keep repeating the word conditional over and over, but in this lecture we are talking about conditional MLE. We find it helpful to have notation and terminology to refer to common objects that we encounter throughout these lectures, so I'm going to start introducing some terminology now that we'll rely on later. The score vector is defined as the function of beta. It is a vector function of beta that is equal to the partial derivatives of the log likelihood with respect to beta. And in the case of Poisson regression, the score vector can be expressed as the vector x times the quantity yi minus e to the x prime beta. It can also be shown, and there are a few more details about this in the notes, it can also be shown that in the case of Poisson regression, the conditional MLE is the solution to the following sample problem, namely, the first order condition is the sum from I equals 1 to n of x times y minus e to the x prime beta. And we find it helpful to refer to this object y minus e to the x prime beta as ui. It's effectively a kind of residual. So this first order condition is saying that the sum of x times the residuals is equal to 0 at the conditional maximum likelihood estimator. And in the notes, I explain why it turns out for this model that the first order condition does actually identify the solution. So it's easy enough to find an expression for the sample log likelihood, and it's easy enough to maximize that in the case of Poisson regression. But what exactly are we estimating? If we don't necessarily believe that the Poisson model is right, and we use Poisson regression nonetheless, how do we know that we're getting anything meaningful or that we're getting anything interpretable? Remember from the theory of conditional maximum likelihood estimation that we talked about in an earlier video that we can define an object called the pseudo-true parameter value that maximizes the expected conditional log likelihood, and somehow that's the parameter that we are consistently estimating if we write down a misspecified conditional likelihood model. But what does that parameter value have to do with our conditional mean function that we originally specified at the beginning of this lecture? Remember, we were trying to solve the problem of negative predictions from an OLS model. We said that's not a great idea if we're predicting a count. We know that counts need to be positive, and we ultimately settled upon this idea of specifying a parametric function m of x and beta such that this function would always be positive. And I mentioned that a very common choice of m in practice is e to the x prime beta. So throughout this lecture, we're assuming that the conditional mean of y given x is e to the x prime beta. All right, so given that fact, and given that we don't necessarily believe our Poisson assumption, what is the pseudo-true parameter value for Poisson regression? Well, we're going to find out in a few steps. First, by iterated expectations, we can write the expected log likelihood as the expectation of the expected log likelihood conditional on x. Let me be very clear here. This conditioning on x is not redundant. You may be saying, but wait, aren't we talking about conditional likelihoods in this video? The answer is yes. So this script L of beta is a conditional likelihood function. But here the expectation is conditioning on x. That is a separate decision that we've made to condition on x. It's not already baked in to the fact that we're looking at a conditional likelihood. In other words, a conditional likelihood is just a function of y and x. We are calculating the conditional expectation of that function given x. That aside, let's proceed to unpack this iterated expectations expression. So, substituting the log likelihood for the Poisson regression model, we obtain the following. Now, we're going to simplify this inner expectation. So we see that we have a y, x prime beta. Now, x prime beta given x is just a constant. In other words, conditional on x, we know x prime beta. So we're going to be able to pull that out front. That leaves us with a conditional expectation of y given x. Similarly, e to the x prime beta is also a constant given x. So we don't need to have an expectation here. And the last term, well, that's a bit complicated. What is that? That's the conditional expectation of the log of the factorial of y given x. I don't know what that's going to be, but what I do know is that it doesn't depend on beta. All right, now, suppose that we were to take the first order condition for optimizing this inner expectation, for maximizing this conditional expectation with respect to beta. In a moment, we'll see why this is a useful thing to do, but for now, just trust me, it's going to be helpful. So if we calculate the derivative using the expression from above on the slide, we obtain the following first order condition. So this says that the vector x multiplied by the quantity expectation of y given x minus e to the x prime beta, that whole product should be equal to the vector 0. At the top of this slide, I have copied the first order condition from the bottom of the last slide so that we can more easily refer to it. So what does this tell us? I maintain that this tells us everything we need to know. Why is that? Well, remember that I assumed that the expectation of y given x takes the form e to the x prime beta for beta equal to this true unknown parameter value beta naught. Well, taking a closer look at this first order condition, notice that if that's right, then I can make the object in the curly braces exactly equal to 0 by choosing beta equal to beta naught. In other words, beta naught turns out to be the parameter value that maximizes the expectation of the log likelihood given x. In other words, for any possible value that x could take on, for any realization of x, and for any possible value of this parameter vector beta, the conditional expectation of L of beta given x must be less than or equal to the conditional expectation of L of beta naught given x. So, taking expectations of both sides, and again, using the law of iterated expectations, what we have just shown is that beta naught is not only the solution to this inner optimization problem of maximizing the expectation of L given x, it's also the solution to the unconditional problem. In other words, beta naught is the parameter value that maximizes the expected log likelihood. Beta naught is the pseudo-true parameter value. So we have shown that if the true conditional mean function really is e to the x prime beta, and if we decide to carry out Poisson regression in spite of the fact that y given x may not follow a Poisson distribution, the pseudo-true parameter value, the one that maximizes the expected log likelihood, is going to be precisely the true parameter of the conditional mean function. Even if our model, the model that assumed the data come from a Poisson distribution, is false. Another way of saying this is that Poisson regression is consistent as long as the conditional mean of y given x is correctly specified. And while we showed this for a particular choice of m, namely e, the result is general. So, provided that we have correctly specified the conditional mean of y given x, it doesn't actually matter if y given x follows a Poisson distribution. This is actually very similar to what we saw in our first lecture when we found that the Poisson maximum likelihood estimator for theta, remember that theta is the mean of a Poisson distribution, that is still going to converge in probability to the mean of the distribution from which the data were drawn if the data did not come from a Poisson distribution. So this is a bit like a regression analog of that result that we've already seen. Now there is a small caveat for those of you who are particularly sharp-eyed. Strictly speaking, I have not shown that beta naught is the unique maximizer of the expected log likelihood. In principle, we could have multiple solutions. For example, if x contained one regressor that was just a linear function of some others, we could run into problems just like an OLS regression. But this is nevertheless truly an extraordinary fact. So this accounts for some of the popularity of Poisson regression. We don't have to believe that the model is right. We can still use it to learn the conditional mean function as long as we specify that part of the model correctly.